Пойдем?
Здравствуйте, коллеги. Меня зовут Дмитрий Черкасов, Ассоциация развития тераностики. И сегодня мы поговорим с экспертами по поводу, а какой циклотрон, какая энергия нужна для развития тераностики, для центра тераностики, и вообще какая ситуация, какой статус с циклотронами высоких энергий. Добрый день.
Михаил. Я уже несколько, можно сказать, десятилетий работаю в области радиофармацевтики. В последнее время работал в ПЭТ-центре, центра Алмазова. Мы еще не касались темы тераностики во время моей деятельности в центре Алмазова, но в перспективе эта тема, безусловно, интересна.
Георгий, представишься?
Добрый день, Георгий Андреев. Я медицинский физик Медицинского института Березина-Сергея, Санкт-Петербург. Мы занимаемся ПЭТ-диагностикой, радионуклидной диагностикой с 2011 года, уже больше 10 лет. И в прошлом году у нас были сертифицированы 2 палаты для тераностики. Надеемся, в скором времени мы принять первых пациентов, делаем первые шаги в этом направлении. Ну и вот в частности установили на производстве, на циклотроне твердотельную мишень по производству галлия-68.
Hello, Jean-Michel. Thank you very much to join us today for this video. Jean-Michel is an expert of IBA and has a huge experience in radiopharmacy market and cyclotron developing issues. So I let you the floor to present yourself.
Hello, I'm Jean-Michél Gitz. I'm an electrical engineer by education, but I've been working the last 20 years with IBA radiopharma cyclotron solution. I was involved in product management and product development of various cyclotrons and targets related to nuclear medicine radioisotopes. I'm also a member of Nuclear Medicine Association in Europe, and I have a few patent and publication related to radioisotope production.
So today's topic, what cyclotron do we need for the teranostics use, and what is the status of 30 MeV cyclotrons in region, because I know that today in our region there is only one machine, 30 MeV, it's, a contemporary machine. То есть сегодня существует только одна современная машина, находится она в Казахстане, в Алмате, на базе Института ядерной физики. Она была куплена и установлена, по-моему, в 2009 году, но по сравнению с теми машинами, которые запускались и работали еще в советское время, в 80-е, в 70-е, даже в 60-е годы, это современный аппарат. I told that we have only one machine in our region of 30 MeV, contemporary machine, rather contemporary, because in 2009, I think.
Already.
Already not very young, but anyhow. So if you have maybe some kind of presentation, yes, I will be glad if you can show the range of cyclotron and maybe tell us a couple of words. What do we need to be in teranostics today to be on the good level of teranostics?
So I would say the good point within IBA cyclotron family is that we are covering various energies, as you see here, well, the name does not imply it, but we have a cyclone key, which is the access machine fluorinating, 9 MeV low energy cyclotron, cyclone cube, which is 18 MeV cyclotron proton beam, the cyclone icon, which is the new version of, as you introduce it, the cyclone. I would write it like this, that is cyclone 30, the 30 MeV machine, and we have as well the cyclone 70. Well, basically, let me see if it's working. Okay, it's working from the other screen. Should work. I will skip this one. Well, the cyclone cube or the cyclone 18 from IBA is cyclone cube is the new version of the cyclone 18. So you have a couple of those machines in Russia. The new machine was designed for the performance, much higher beam current, and flexibility of or the capacity to select the energy of at least 2 extraction ports, high uptime for people that want to produce 24/7, reliability with some double equipment, double ion source, double stripper per extraction, and 4 vacuum pumps for high efficiency. As it's pretty well known in terms of teranostic, having a companion diagnostic drug. We do have a liquid target production of copper of gallium-67 first of all, gallium-68 sorry first of all, and we have introduced as well liquid production of copper-64. This liquid production is, let's say, the most easiest way to mimic the fluorinating FDG production. You irradiate a liquid, you transfer a liquid, and later on you make cartridge purification and then labeling. So you see here various tracer like PSMA, DOTAT, DOTANOC, or copper ATSM, which are in use today for nuclear medicine theranostic.
So for the general understanding for our colleagues who are watching this video, we are talking now about maybe 2 major isotopes that we can use in theranostics. It's all metals. One gallium with 68 minutes of half-life, gallium-68, and another copper 64. Also we can use it for diagnostic, and the half-life it's much more longer, as 12 hours. So it gives us huge potentials using the ligands that required many hours to uptake.
Yes, it of course can be used for a slow biological process, ligands that will take time to find their target, or for some producers which are looking today at a distribution market from centralized supply. It could also, I would say, alleviate the issue of the short-lived gallium-68, whether you can distribute over the long range a copper-64 from a centralized location to a country or a region.
So as we discussed in our previous video, link you can find under the video, to produce gallium-68, there is no issues to do it using the modern or not modern medium energy machine like Cube 18, for example, or Cyclone 18-9. But what we need for Cuprum, because I think it's very interesting way of developing of theranostics.
Yeah, liquid target for copper-64, or some people are also working with copper-61 PET isotope. It's another copper, I would say. It's exactly the same process of irradiation of a liquid, purification on cartridge. But okay, we are speaking of another target material and then another isotope. But in terms of equipment, it's a dedicated liquid target, a module called Sintera extension for purification, and then maybe labeling onto Syntera or labeling onto another module.
So if for gallium-68 the best energy is 13 MeV around this, yes, what is the best energy for liquid copper-64 production?
Almost the same, because the peak of production for a nickel proton nuclear reaction is also pretty low, in the range of 12 MeV. So if we have the cyclone cube custom energy with a small foil, we are in the right energy onto the liquid target. So it's also an asset, I would say, to have the variable energy cyclotron. You are reducing the load onto a degrader.
Mm-hmm. So we can use, for example, cube with various energy and with. Okay, I see.
But as we explained into some other discussion and previous video, of course, liquid targeted somewhat producing, I would say, less isotope, because you dilute the material into a liquid, and we do have as well. A solid. Let me see. Yeah, this is the right one. So we have a high current. We call it compact solid target for PET isotope production, and then in this one we use a degrader foil and preferably a beamline, where we can shoot on the target with up to 150 microampere into a copper plate that you see around here. If you so the target plate is around here. This is this angle target, and we shoot through various degrader up to 150 microampere. There you have a solid target isotope, a solid target material, and you have a higher production rate, and you multiply by higher beam current. So for us, this is the, I would say, the commercial way of producing a copper-64, for example.
Okay, and what about purity and materials we are using for that?
Well, purity of for the production of, if we speak about copper-64, is enriched nickel-64 at 99% or so, and then the target plate is sent to an automatic chemistry module that will dissolve and purify the copper-64 out of the nickel target.
А сколько нарабатывают меди, ну, там, в час, например?
Well, about this, because regarding gallium, technology is clear. It's commercial available, we can buy it, we can install it. But what about copper-64? Is it available, and what is the EOB level for this target?
In liquid or solid? So liquid form is available through IBA as so far a collaboration, and I have to say I do not have the value, but it's in the range of a few hundred millicurie per run. So it's really for us local scale production of copper-64 to be able to introduce copper-64 into your hospitals, into your research, or even clinical use. With the solid target, with 150 microampere into a solid nickel-plated target, you have production range of in the range of 8 curie of copper chloride after a day-long beam, so 6 to 8 hours. So due to the half-life of the copper, it's really a centralized production.
Could you please repeat the last phrase? How many hours and the activity?
So usually it's 8-hour production times 800
8 часов.
50 microampere. So let me do the quick math of this, if you do not mind.
And we need minimum 150 microampere Cyclotron, okay.
То есть он фактически работает
So
постоянно.
we are in the range of 7-8 curie of copper chloride.
7-8 кюри хлорида меди, но это очень большие активности,
Очень
это огромные.
Ну, в общем-то, с учетом большого периода полураспада, целесообразно нарабатывать такие количества.
Особенно ты можешь экспортировать. То есть,
Конечно,
в принципе,
в другие учреждения.
1-2 таких систем достаточно для того, чтобы реализовать потребность рынка в 64-м МИБе.
По крайней мере, европейской части России это точно.
Ну, тут еще нюанс, я думаю, с радиохимией, потому что если у галлия достаточно все просто, и ты фактически достаешь пептид из коробочки, и это
через час получаешь препарат.
Как кофе 3 в 1 практически. Все-таки, если мы работаем с медью, я полагаю, что это уже более сложные молекулы. Возможно, это работа с антителами.
One more comment, it's this kind of high power solid target, even if we say compact, it's not easily upgradable into existing sites. You still need some room to install such a target, preferably with an external beamline on the cyclone cube, and it requires a large hot cell with manipulators to handle, first of all, such level of activity, and then to handle the...
Ну, то есть это действительно совсем другой уже уровень технической подготовки не только самой машины, самого циклотрона, но и, в принципе, радиофарма,
и работы.
Производства и работы.
Технологического оборудования.
То есть если мы выходим на выходим на уровень 64-й меди, то мы должны специальным образом проектировать объект и планировать этот объект.
То есть это нужно... Это актуально, конечно, для тех организаций, которые еще в стадии проекта.
Разумеется. Ну, вот по моему мнению, если сегодня создается современный онкологический центр, который будет развиваться в будущем, то вот у такого центра обязательно должна быть хорошая кухня, хорошая база радиофармацевтическая, с открытой архитектурой, которая позволяет делать вот такие вот небольшие независимые лаборатории, в которых уже можно проводить работу.
Может быть, не столько архитектура, то есть архитектура должна быть в проекте, то есть она, безусловно, должна быть уже продумана уже на стадии проекта. То есть не так, что у нас есть поле, на котором мы можем засеять одну или вторую культуру, а мы уже должны планировать, что будет именно там медь.
Разумеется. И желательно иметь какую-то гибкость, на случай, если действительно какие-то изменения нужно будет делать уже.
Если вы запланировали медь, то остальные радионуклиды там тоже можно будет получать.
Окей. So we are talking about the site readiness for this technology. If we are talking about gallium, it's like a coffee pack. So you open, you mix, and you drink. For the copper level, you need a really dedicated laboratory with good architecture and quite wise technological way of preparation.
Yes, and train people and skilled people, but due to the half-life of copper-64, it could be into a more centralized approach. So you may have one large center for the region where you distribute copper to hospitals, but to make a distribution, again, it's the circle issue. You need to have a need by the nuclear medicine doctors. You need to have approved tracer which have a clinical interest. And then someone has to provide the copper-64.
Yeah, it's like what should be the first, egg or chicken, and what about doctors? So it's our goal of our Theranostic Association and this video to enlarge the knowledge about the possibilities.
To start small, let's say that IBA has some smaller target in the range of 30-50 microampere, which are semi-automatic, I would say, or semi-manual. Someone needs to load various target coins into the cyclotron bunker, but then they can recover the coin after irradiation by automatic transport and then do the processing. Probably easier to install, but anyway, it's a solid target process and you need space into the hot cell to put the chemistry module and so on. So I've here only proposed on the slide, it's only the high current compact, but we have two other smaller targets that could start, let's say, the copper production and probably into existing centers.
Хотел уточнить, вот это медь, это на твердотельной мишени.
So no, we are talking about liquid target.
And the target plate. То есть какая-то пластинка, ну.
Мне кажется, мы обеими технологиями можем пользоваться.
Jean-Michel, we can use both technologies to produce copper 64 solid and liquid.
Yes, even on the same machine, you can have a small liquid target that is, of course, obviously producing a low quantity of copper chloride, but that could feed the doctors for their research or clinical use, and it could be at later stage upgraded at another extraction port of the cyclone cube with a solid target, high production, or when it is needed. You will probably do copper 64 once a week.
Can we jump back to the slide with cyclotron family?
Пока мы не вернулись, у меня есть еще один вопрос. Насколько мы можем сократить время бомбардировки для получения меди 64? Какое минимальное время?
There is a question from Георгий. Can we reduce the time of radiation for copper 64?
Yes, you of course you can reduce the time, then you reduce the end of beam quantity onto the solid target,
but it's not the linear, how to say?
In first approximation, yes, in first approximation, 3, 4, 6 hours, 8 hours, it's almost still in the linear phase of the copper production. So we can provide you some data, but roughly, if you halve the time, you halve the end of beam value.
Okay, so it's a good slide because here you can see the names of cyclotron, but you don't see the energy of this cyclotron.
Exact.
But yeah, on the left there is a small machine presented this year. I think in the beginning of this year during Arab Health. Very small and very compact machine, but it can use only for basic onco needs. So only for fluor 18 or N13. So maybe basic for oncology and cardiology.
Yes, this is probably our IBA answer to a small local hospital which do not have a lot of patients into their PET scanners, and that will run this machine, if I may say, like a generator to make a little bit of fluorinating into remote area where you will never have a large production center or where you cannot ship FDG because of the half-life.
But if we would like to jump in the theranostic area, we need minimum 18 MeV machine or minimum 13 MeV machine with 150 microampere.
So mid of last year, we have introduced a new cyclone icon.
Yeah, and I'm sorry, it was my next question. And what about high energy machine 30 MeV? Because unfortunately, it's not, I could say, not popular today. But what flexibility, what options it can give to us to develop radio diagnostics?
So the new name is Cyclone Icon, but you see the I don't want to do that. You see the energy range of 30 MeV maximum, but we have lowered the range into the machine down to 13 MeV. So it's pretty wide range for such a machine. It has all the features of, not to be too technical, but external ion source cyclotron, which are very efficient in terms of acceleration transmission, so low loss into the machine, very high extraction efficiency of H-, and so we can reach very high current on those cyclotrons. And at the same time, we make the machine very compact. When you see 30 tons into such a small cube, or square surface, so it's much better than the Cyclone 30 previous high energy machine from IBA.
I would like to add, because on this slide you don't understand the scale and the comparison between, for example, 18 MeV production site and 30 MeV production site, because usually people, when they see 30 MeV and 18 MeV, they are thinking that there is only 50% of difference. But actually it's not 50% of difference. There is quite huge difference in maybe about 5 times. This machine 5 times more expensive, and or 4 times more expensive, and this machine should be installed in special, I would say, special site. Bigger site, and from technical point of view.
Yeah, the construction around the machine, as you see here, those are called beam lines. Once you start shooting at very high current, namely 400 microampere onto a solid target, it's better to isolate the target into dedicated bunkers, concrete vaults. So here you have probably the size which is 5 times bigger than the PET cyclotron bunker. So it has a cost of investment into the building, it's true. But well, the production range and the production rate is much higher.
But can we back to the issue for what we need this machine? Because we can see that the investment rate and the capex rate maybe 5 times bigger than for 18 MeV cyclotron. And in parallel, I would like to ask Georgi, because it was a previous slide for Copper 64, regarding your center, because you are now doing the cutting edge teranostic and oncology center. I think it will be most charged biotechnologies center in Russia. What about Copper 64? Do you have an access for this technology in future, or it's maybe?
I believe with our commentary system, yes, we will have with the solid target.
With solid target,
yes.
Okay, so this solid system you can use in future for the Copper 64.
It's also quite universal, yes.
And you need additional hot cell, I presume, with manipulators.
Yes, in terms of post-production, we need the complete set of hot cells and equipment, so it's extra space. But to make a bombardment, it's possible with this target module.
Okay. Well, Jean-Michel, could you explain what
yes, so here it's an open view of the cyclone icon. So it's a true variable energy cyclotron where you extract by a movable stripper. Let's say, okay. And on both sides, you have 3 exit ports. One exit port is dedicated to 18 MeV proton beam, namely onto this kind of machine, you can attach at least two fluorine target at high current, like the IBA near-taconical 16. So in dual beam mode, you produce 30 curie of fluorinating in 2 hours. And then you have the 2 other extraction ports going to the beam lines and to the various targets that can be installed on the machine. In the range 30 to 13 MeV, with a multi-purpose solid target. You will have access, of course, to copper 64, zirconium 69, and you can also have access to some SPECT isotope, the one that are produced at 30 MeV, as well as.
Do you have a list of isotopes in your presentation?
Yes, not on this slide, unfortunately. So I should switch to another one. If you give me 2 minutes, if I can find it, because I have also.
Сколько мишеней одновременно можно облучать?
Ну, насколько я понимаю, там 2 вывода пучка в разные стороны.
Всего 2.
Да, и из
я понял, там они
в конце каждого вывода тоже,
соответственно, можно фактически это вот по 3 слота, то есть там 3 слота и здесь 3 слота.
И в какой-то из слотов можно ставить целых 2 мишени. Они будут одновременно облучаться.
Нет, а там 2, там идет, там у него одна специально на 18 МФ, как бы вот уже задана, и это для ФДГ, ну, для фтора. А 2 от 13 до 30 с переменной энергией. И, соответственно, там тоже с противоположного конца тоже. То есть фактически 4, но облучать можно только 2 мишени.
А в 2 направления одновременно пучок выводится. А сколько мишеней одновременно можно облучать, это вопрос. Давайте, может, зададим вопрос?
Да.
Jean-Michel, how many targets we can irradiate in the same time on this cube machine? Icon machine, I'm sorry.
And any of negative ion cyclotrons, they can do dual beam, but not more. So 2 targets at the same time with the same energy.
Only 2.
2 мишени. 2 target maximum, okay.
And then you should see now a cyclone family with isotopes that can be produced on the machine. So cyclone 30 MeV now is replaced with the cyclone icon production cyclotron or proton beam mode. Everything that is available at, of course, lower energy with liquid target, fluorinating, even gallium, solid target copper, can be translated to the same target on the cyclone icon. I have a special mention for actinium-225, which is in between the 2 cyclotrons. This one has a very strong interest today in terms of alpha therapy, but it's not an easy target material to irradiate. People have to put their hands onto radium-226, which is a radioactive isotope, and encapsulate this into foils and form a solid target with it. But in theory, this is possible to do either with the 18 MeV or with the cyclone icon or cyclone 30.
So in general, we can say that this machine will give an access, open the door to the therapeutical isotopes, not only diagnostic.
Not only diagnostic, indeed. There are still some people looking at the indium-111. I think thallium-201 for cardiac studies almost disappear everywhere in the world, but it was a large production of the Cyclone 30 machine in the past. Nowadays, special interest on germanium-68, which is the parent isotope of the generator. And this one is produced on 30 MeV proton beam mode, dual beam, high current, Cyclone 30 or Cyclone Icon, if I may say.
So this isotope using to charge generators, germanium gallium generators.
And you see it here as well on the high energy Cyclone 70, which is the way to produce two parent isotopes, strontium-82 for a cardiac generator doing rubidium. Probably it's not well distributed in Russia and not really in use in Europe. It's really starting in Europe, the strontium rubidium. The variable energy machine can produce iodine-123 gas target as well. And it's also a way to produce germanium-68 with a metallic target.
What is the status with this therapeutical isotopes? Because it's most of interesting. I mean, alpha-emitters. It's the future of teranostics.
Alpha-emitter for me indeed seems to be the future of therapy due to uniqueness of alpha-emitters. Very strong biological effect. Very effective in killing the small cancer mass. So probably the best way to attack small metastasis tumors, small mass of cancer cell. But nowadays the availability of those alpha emitter is pretty low. So a lot of people are looking at the actinium-225. That can be produced with proton beam. There is a limited supply of actinium from what we call thorium generator, but this is a really long-lived generator and you have to wait a lot of time to get a little bit of actinium. So people are nowadays looking at actinium-225 with proton beam.
And you need special transport because this is very strong weapon, but you need very good transport for this weapon.
Yes, so far I know that there are some discussion with at least European authorities and regulators on how to disseminate, distribute actinium-225 and what will be the level of control on those alpha emitters. And there was another one which has a very interesting behavior. It's called the astatine-211, which is a single alpha emitter. So to some people, and I'm not a nuclear medicine doctor, but to some people, a single alpha emitter is probably better in terms of radiation dose to the humans than multiple alpha emitters, because you have less risk of the isotope leaving the vector and leaving the target. Probably Dmitry, you can better explain than me. But this astatine-211 is also, I would say, very scarce supply, because it can only be produced with a 30 MeV alpha beam machine, which is a special machine. IBA has one in this range, which is called the Cyclone 30 XP. It's a proton and alpha beam machine that can produce this astatine-211. Strong interest with a lot of researchers in US, and there is nowadays a consortium starting in Europe with various centers that have access or that bought an alpha beam machine to produce this astatine-211.
Спектр излучения у астатина более узкий.
Там, я так понимаю, что одна альфа-частица выпускается, в отличие от нескольких с разными энергиями.
Цепочки.
Да. Ага. Ну, да. И за счет этого более стабильные показатели.
Ну, по крайней мере, нет возможности, ведь разные элементы проявляют разные свойства. И если, допустим, актиний превратится в другой элемент, то он пойдет распределяться уже по другому механизму.
По своему пути. Да.
А астат Он как нацелен, и туда только он и пойдет. Я как понял, вот у меня какой вопрос. Они оценивали такие риски, как содержание альфа-эмиттеров в других радиофармпрепаратах, ну, это может быть бета или гамма.
Диагностических?
Диагностических, любых других. Очень жестко регламентированы. Там должно быть там 3-4 порядка. То есть есть возможность, то есть они оценивали риски загрязнения альфа-эмиттерами других препаратов, которые изготавливаются на циклотроне. Но ясно, что здесь мишень вообще должна быть одна. Ну, под, допустим, актиний. И ни под что другое не может использоваться. Но вместе с тем, через какие-либо коммуникации есть возможность попадания альфа-эмиттеров в другие мишени.
Good question, Jean-Michel. There is a risk of alpha impurities in, for example, icon machine when you are trying to produce other isotopes on the same machine. We are not talking about the same target, but
well, by careful design of the system, and because we have those long beam lines, we would like to avoid any kind of contamination inside of the machine. It's true. That's why we have those long beam lines that isolate the target far away of the cyclotron. With astatine, 211 is probably at some point less dangerous because it's only a 7-hour half-life isotope. So even if you have a contamination with astatine 211, well, you just can wait. If people are working with actinium-225 with a radium-226 target, then of course the target encapsulation, so putting the target into multiple foils and running the target with a lot of precaution, so with enough low beam, I would say, because their damage onto a radium actinium target can be dramatic, even if you have beam lines and you try to avoid internal contamination.
Okay,
it's probably one of the issues that will prevent actinium-225 to be produced into, I would say, small clinics or hospital, even if they have the 18 MeV cyclotron on site.
Okay, thank you. Can we dream about the future, for example, and what will be in 3-5 years, maybe with this isotopes, or it's hard to say at this stage, and it's only a practical way to understand it.
The dream of teranostic, first of all, looking back to try to predict the future, I think the dream will try to mimic the success of the lutetium beta emitter for some neuroendocrine tumors. Probably that gallium diagnostic, due to its short half-life, is not the best. You know that there are now fluorine PSMA for prostate cancer diagnostic. And nowadays there are people working on coupling a therapeutic isotope with the PSMA for prostate cancer. Probably this one has a high rate of success. I still believe that...
you mean PSMA 607 or something like that?
One of the PSMA for prostate. It's well known that it's one of the major cases of cancer for men. It has always an issue with all those metastatic lesions. And so getting the right diagnostic and the right therapy will be important. So looking at the success of lutetium-177 beta emitter for a neuroendocrine tumor, if someone can speak about the next therapeutic coupled with PSMA, then I think there will be a kind of huge success. And what I understood from the doctors, it's also the effectiveness of alpha emitters that can be very interesting, even with low dose injected to the patient, but it has very high efficiency. provided that actinium-225 or astatine-211 can be made available by production center, centralized production center. I think it will be the way to go. Centralized production center for a region or a country.
So you mean that, for example, if somebody in Germany, for example, will start this production, they can feed all the centers by astatine, for example, in region.
Yes, in the region, yes. Astatine is 7-hour half-life. It has not a big production rate, but it's pretty efficient. And so we think that a network of cyclotron will be needed for astatine-211. Actinium-225 has a longer half-life and range of 10 days. It can be, of course, shipped with, as you said, some precaution and authorization from the agency because it's really a toxic alpha-emitter. And so I believe that we will see at least 2 of those modalities that will come onto the market with some specificities, but alpha-emitter will probably be the next choice after the lutetium or a beta-emitter. Beta-emitter for large tumor mass or large metastatic disease, and probably 1 or 2 shots of an alpha-emitter for a small metastatic disease, just to be sure that you have a kind of cancer-free period. But this is what I understood from doctors.
Let me back to my question. When do you expect the beginning of epoch, of era of alpha production on cyclotron, or it's done and but we don't know about it? I mean, from our side, not from your side, because you're most engaged in many worldwide projects, and you certainly know better than us the worldwide situation, and it's very interesting to see the global experience.
It's not done yet, I have to say. Looking at the number of clinical studies in the US and in Europe related to alpha therapy, actinium-225, namely, we clearly see a very high number of clinical studies, and we see a strong interest by large pharma companies to have access to those isotopes. So as soon as they start clinical studies, they want to have a backup for the production. And so there are nowadays commercial producers that are asking more and more, and they are starting production or thinking of production of actinium-225. In any case, building business plan, getting the money, constructing the center is taking 2 or 3 years.
And this is a big toy for big players like Curium or Novartis, for example, or
so far today, it's big toys. Yes, actinium-225 for research is mainly produced today by the small stock of thorium generators, and it's almost enough to provide research and a little bit of clinical doses. But probably in a few years we will see a need to have actinium-225 large-scale production. I'm already aware of some sales with the Cyclone Cube and Beamline, which are dedicated only to actinium-225 production.
So you mean that energy and current will be enough for actinium production on Cube machine? Medium energy, okay.
Medium energy, probably not into a very large scale, but as I said, pharma companies are today looking at cyclotron companies or players that can guarantee that they will provide actinium-225 in a certain quantities in the 2 years to come, I would say.
I can explain again for For those who don't know about the cyclotron market and price range, sometimes the medium energy machine price could be the same, for example, as a price for target for high energy machine. So this it's not double. It's sometimes it's 5 times or 10 times more expensive. So in some cases, it's easily to buy 2-3 medium energy machine and using it for different purposes, goals. There is this practice in European institutes. I think in Amsterdam, BV, for example.
Yeah, there are already some commercial companies that are doing copper and zirconium onto their PET cyclotrons. I have to say that usually, even Coimbra in Portugal, usually they have multiple cyclotrons on their site. As you said, BV cyclotron in Netherlands, they have 3 18 MeV machines, 2 of them with beamline and solid target to have production of zirconium mainly, but they are also producing other isotopes. And so they have a kind of backup into a centralized production center.
What do you think about long-term expectation from 30 MeV machine? Because as we see, for example, as we are talking about germanium production in Russia, they are using a 50 years old machine and keep feed the market with this isotope. And what do you think about the future of 30 MeV Icon, for example, in 15 or 20 years, or it's too early to have this?
It's not too early because we have already at least one sales of Cyclone Icon, at least one, where we know that it's only dedicated to germanium-68. So the machine will run 24/7 only to provide germanium-68 to a producer. Because due to the increase of the germanium generator capacity, we are speaking about 20 millicurie generator, 50 millicurie generator, 100 millicurie generator, and the market demand for the gallium DOTA compound, companies are nowadays trying to get more germanium-68 into their generator line. So we have companies that are buying the new Cyclone Icon machine only for germanium-68.
Okay, I see.
But as I said, it must be a high current machine, high current target, and it should be dedicated for commercial quantities. It's like 4 or 5 days of continuous beam time onto the target.
Okay, we are looking for the nice future of alpha and other isotopes with high energy machines.
Но вопрос однозначный, что одновременно на одном циклотроне нельзя получать альфа-эмиттеры и другие эмиттеры.
So the question we cannot produce in the same time on the same machine alpha and other emitters.
Необходимо обслуживать все равно мишени, когда идет обслуживание, вскрываются мишени, и полностью контаминацию альфа-нуклидами нельзя исключить других. Я очень много работал с альфа-нуклидами.
And we cannot exclude alpha contamination during the service procedure because Mikhail has an experience with alpha emitters.
Но, возможно, целесообразно иметь действительно для специализированного онкологического центра специальный циклотрон, который будет заниматься только альфа-нуклидами, если это интересно.
Maybe it makes sense to have this special dedicated machine for the special oncology institute, for example, that are looking to develop alpha emitters.
Probably at some point this is what will happen. consortium will use a dedicated machine for their alpha isotope production. Yes.
Окей. Егор, как ты думаешь по поводу альфа? Насколько ваш объект в перспективе будет использовать эту технологию?
Ну, начнем с того, что радий 223, да, это уже как бы такой достойный пример альфа-эмиттера, и он широко во многих клиниках используется.
И у вас тоже?
Вот я говорю, что как раз получили сертификацию на 2 койки, да, начинаем.
Ксофига.
Ксофига, да.
Ну, Ксофига, он не циклотронное производство.
Да, но...
Изначально радий...
Это компактно, ампулы, флаконы, все плотно. А вот здесь...
Безусловно, альфа-эмиттеры, благодаря своей высокой относительно биологической эффективности, да, за счет высокой плотности передачи энергии, за счет двунитевых разрывов ДНК, они, то есть будут в скором времени, наверное, все больше и больше занимать умы радиотерапевтов. Другой вопрос, что насколько необходимо иметь в клинике, в онкологической клинике вот такой циклотрон, там, скажем, 30-мэвный, наверное, это все-таки машина не на каждый день. То есть вот этот слайд, который мы обсуждали достаточно долго, он показывает, что циклон 18 или циклон Cube – это машина на каждый день с широчайшим спектром изотопов. А 30 или 70-мэвные машины, наверное, это действительно не для клиники, а для производственных, научно-производственных небольших компаний, которые бы могли централизованно поставлять сырье для дальнейшего синтеза либо биотехнологическим компаниям, либо в клинику, потому что, действительно, и обслуживать. Да.
Либо крупный какой-то университетский комплекс, который может себе позволить именно управлять и эксплуатировать такую машину.
Вы знаете, я еще раз говорю, что это должен быть, ему совершенно абсолютно, знаете, такому, имею большой опыт с альфа, это должно быть отдельно, то есть это должен быть и целесообразно, вот как сказал Юрий, что это должно быть какая-то централизованная поставка, период полураспада позволяет поставлять, как Ксофига, поставляют по всей стране.
Да, большой регион.
И это должен быть один центр с одним хорошим циклотроном, который обеспечивает всю страну в данном препарате. Тут
вопрос не только циклотрона, вообще всего, вы правы, это совокупность и подготовки специалистов, и уровень инжиниринга, и в принципе реализация такого объекта, как мы поговорили в начале, такой объект минимум в 5 раз дороже, в 5 раз больше, несмотря на то, что вроде мы сравниваем 18-мэвную машину средних энергий и 30-мэвную машину, но мы видим, что разница в цене не 50%, как иногда думают люди, что если ты берешь машину 30 МЭФ, то ты должен доплатить, соответственно, 50% цены.
За 12 МЭФ.
Да, за те 12 МЭФ ты их докупаешь как электричество на даче. У тебя было 15 киловатт, стало 30.
Как первая, вторая, третья космическая скорость.
Да. Нет, тут совершенно нелинейная зависимость, и действительно машины, которые требуют абсолютно другого подхода, другого уровня инжиниринга.
Не столько инжиниринг, сколько должны быть потребности в этом. То есть один центр не сможет потреблять столько активности, чтобы это было экономически эффективно. То есть это нужно, чтобы это действительно было буквально 2 центра на всю страну, которые бы обеспечивали.
Это мы, возвращаемся к такому организационному вопросу, очень важному. Это так называемый нетворкинг, это открытое взаимодействие между различными площадками, того, чего, мне кажется, нам очень часто не хватает, когда люди в учреждениях вместо того, чтобы максимально открываться и искать коллаборации, наоборот, закрываются и пытаются иметь свою ферму со своими завиряемыми растениями, хотя в современной технологии это просто невозможно.
Вот хочу сказать, что, допустим, с фтором это возможно, с углеродом возможно, с альфа-эмиттерами это невозможно. Практически невозможно работать в одном учреждении, как я вам сказал, на одном циклотроне нарабатывать и то, и это, избегая контаминации альфа-нуклидами. Поэтому здесь сразу требуется особый контроль качества всех остальных радионуклидов на содержание альфа-нуклидов. А это по времени это очень непросто, потому что там их содержание должно быть относительно активности 10 в 10 минус 10. То есть это нужно еще проконтролировать с такой степенью точности содержания альфа-нуклидов. Это практически невозможно. Поэтому здесь вот ни одна клиника, я думаю, даже на Западе не сможет окупить отдельное производство, допустим, альфа-эмиттера в каком-то одном центре. То есть это действительно уже, это не просто, что нужно объединяться, чтобы было бы легче, а это просто невозможно экономически, нецелесообразно делать это. И это культура производства, вы знаете, вот я все-таки работал, действительно очень много работал с альфа-эмиттерами военного назначения. Я хочу сказать, что это совершенно другая культура, то есть вот нынешний уровень, ну, допустим, в центре Алмазова, ну, я думаю, не только в центре Алмазова, работа с радионуклидами не позволяет работать простой переход к альфа-нуклидам. Это совершенно другие, должна быть совершенно другая культура производства и должна быть совершенно другая организация производства.
Да, люди, к сожалению, быстро привыкают к простоте, к безопасности, к комфорту.
Это, допустим, я могу привыкнуть, а они никогда не работали, им привыкать-то не.
We are talking about the level of knowledge and the level of competency to work with alpha, because it's a completely the different story. It's not a coffee machine.
Я хочу сказать, если вы будете работать с альфа-нуклидами, вы понимаете, это надо настолько все четко продумать и воспитывать и проводить тренинги.
It's a completely new way of quality of safety assurance and etc. Too many, I would say. It's not the second step on the stair. It's 5 floors up, maybe.
Except if those isotopes are produced into centralized supply and that you get a vial with a kind of easy procedure like shake and bake. And
It's actually what we are talking about. Yes, ну, то есть если действительно есть какое-то централизованное производство и уже потребитель получает абсолютно как бы
готовый для инъекции,
безопасный, закрытый как конечный продукт. Ну, я думаю, что тема циклотронов разных энергий, какие циклотроны, для чего нужны в тераностике, в принципе, мы эту тему сегодня раскрыли. И неплохо как бы подсветили эту проблематику. Как вы считаете? Или что-то мы не затронули?
Да нет, в общем-то, все так, мне кажется, хорошо обсудили. Конечно, перспективы очень интересные, которые представляет 30-мэпный циклотрон. Вопрос в том, что действительно должна быть достаточно хорошая клиника с несколькими сканерами, ПЭТ-сканерами, томографами, чтобы окупить все издержки на содержание этого циклотрона. То есть это должна быть действительно большая, очень централизованная медицинская организация с хорошим потоком пациентов. А возможности просто замечательные.
Ну, я еще раз хотел поблагодарить Михаила Петровича.
Михаил.
Большое спасибо за участие в сегодняшнем мероприятии. Георгий, всегда рады видеть.
Спасибо за приглашение.
And Jean-Michel, thank you very much for this presentation and this opportunity to know more about cyclotron world from how to say from the first from the first row, from the developers.
From the factory floor.
Yeah, from the factory floor.
It was nice seeing you and talking to you, colleagues and friends. And well, let's see the outcome of this.
Yeah. See you. Thank you very much.
See you.
Thank you.
All the best.
Thank you very much.
Bye.